0,5 acho que é de 90 graus.
0,5 është çfarë?
Sinusi ka 90 gradë.
Sinusi ka 90 gradë është 1.
Se ne kanë 3 kamsh Pitagorës, profesor, me një kamsh që vetë është edhe 2 katetet.
Një është sinusi 30-ës, tjetra e 60-ës.
Okay. So, what do you think about this triangle? What is the cosines and sines of these values? Now, what was the matrix? This was 1, 1, 1, 0. Was this the matrix?
1 minus 1, 1, 0.
Is this minus 1?
Both.
Okay. Because I don't remember, so we have here 1 minus lambda minus 1, 1, 0. And sorry, this is minus lambda also. So the determinant of this one is equal to 1 minus lambda times minus lambda plus 1, this is 0. Then here we obtain the following. We get lambda squared minus lambda plus 1, this is 0. So this is the second order polynomial from which we want to obtain two eigenvalues. And the eigenvalues, we can write them lambda 1, 2, this is equal to minus b plus minus square root of b squared minus 4ac over 2a. And this is equal to minus b, this is 1, plus minus I square root of 3 over 2 plus minus over 2. Okay? Now, let's see what happens if we apply okay, so this is the let's take a vector x0. Well, let me write this right away. So can you give me a vector, but which is a small one, not 13, 4, like 1 minus 1 or some other vector? Let's consider 1, 0, okay? If we have a vector which is 1, 0, we can multiply this one with 1, minus 1, 1, 0, and what do we get? Is it? I believe this is correct. So this is equal to a times 1, 0. Okay. Then we can multiply this again. 1 minus 1, 1, 0 with a vector which is 1, 0, and this is equal to what is this? Actually, this is always. Is this the matrix I gave to you? Okay. This should be plus 1. Yeah, this is only the only possible case. So what we get here, this is 1, 1. Is this correct? 1, 0. No. Sorry. So I have to multiply with 1, 1. Sorry, I have to multiply with 1, 1. Then I get here 0, 1, and this is equal to a squared times, okay, because I was multiplying with this one. This is 1, 0. Now it looks better. So we started with x0, which was 1, 0. 1, 0 is here. Is this vector, right? Then, what is a times 1, 0? So this is x0. This is a times x0. Then let's multiply again by a, which is 1 minus 1, 1, 0 times 0, 1. Actually, wait a second. So yeah, the next step, a squared times the initial vector is 0, 1. 0, 1, it is this vector here, right? So this is a squared times a0, x0. So we observe that if we apply this matrix to a vector, we are only rotating it, right? So this is what we're doing. And then if we multiply this with 0, 1, we get, what is this? This is -1 and 0. So -1 and 0, this is a cubed times 1, 0. So the initial vector, so this is what we're doing. -1, 0 is this vector here. So apparently, this is what we're doing. So we can even try to draw the path. So we go like this, it goes like this. If we multiply again, 1, 1, -1, 0, we get -1, 0 here, -1, 0. This is equal to
-1, -1.
-1, thank you. Okay. So we get here, we get this vector. If we keep doing the same thing, we apply now 1, -1, 1, 0. We multiply with -1, -1. So we're just observing how we are going to rotate this vector. Now we get, I believe this is 0 and this is -1, 0, -1. So we get this vector here. And by the way, this is a squared times x0. This is a cubed times x0. This is a to the power 4 times x0. Here we have a to the power 5 times x0. So this is what we get. And then let's multiply again. We have 1, -1, 1, 0. We multiply this with where we are at. We are at 0, -1, 0, -1. This is equal to, this is 1, and this is 0. So this is 1, 0, and this is equal to a to the power 6 times 1, 0. So it looks like we came back here. So this x0, this is equal to a to the power 6 times x0. So that, what can we take from here? It looks like so in this case, we have a and we have x0. So we can also easily calculate what is a to the power 37 times x0. So what is this? We know that multiples of 6, we're going to get x0 again. So we can have here a times a to the power 36 times x0. This is equal to a times x0, because this is going to give x0 again, right? So what we get then, we get this vector. So this is also equal to a to the power 37 times x0. So we have a cyclic order. Now, what do we observe here? We see that we do 6 different rotations, right? So on average, if we do 6 angles, what is the average? If with 6 rotations we cover 360 degrees.
That's right, 60.
It's 60, right? So 60 is equal to cosine of 60 degrees plus I times sine of 60 degrees. Okay. So these eigenvalues of this specific matrix, what they are, they represent a rotation by 60 degrees. Okay. And this one, we know by Euler identity that this is equal to I times e to the power I 60 degrees. Because we know this property, which is e to the power I theta, this is equal to cosine theta plus I sine theta. So apparently, and we know also that the eigenvalue, so we know this equation. If we have A, matrix A, times the first eigenvector V1, this would be equal to the lambda 1, so we times V1. Now, this might be a little tricky because the multiplication of this E1, this might not be in the real domain. This could be in the complex domain, but this is something that you can have a look at this problem as a homework. But what is interesting here is that what the matrix does to a specific vector, it can also be operated by the by the eigenvalue. So on a vector, whatever a matrix does to a vector, this is equivalent to multiplying that vector with the eigenvalue. And probably this kind of proves itself of why this is possible. Now, what could be interesting, we can also observe that these angles are not 60 in fact. So this is like 45, this is also 45, we have a 90 here, 45, 45, another 90. But in principle, we also learn that for this specific matrix, we get the following, we get that a to the power 6 is equal to the identity matrix 1, 0, 0, 1, and a to the power 3 is equal to -1, 0, 0, -1. So we get these interesting properties. And it is interesting also to look at the eigenvalues of these two, okay? And it can also be interesting to look at the eigenvalues not only of a to the power q, but a to the power 6. But you can work this one and see what would be the well, you can check for a, we did it. For a squared, you can calculate, so you just check what are the eigenvalues of a squared, eigenvalues of a cubed. I think they are mostly clear over here, where the eigenvalues of a, okay. We have not done a to the power 5, but we know exactly what are the eigenvalues of. So out of all of these, we know the eigenvalues here, we know the eigenvalues here, we know the eigenvalues here. It could be a good exercise for all of you to also check what could be the eigenvalues of these other matrices, and if there is any difference. Now, I just wanted to have a look at this example, just to see an equivalence between this one and the eigenvalue for the matrices or how they operate on vectors. Yeah. One interesting exercise for you, it would be the following. Can you find a vector x0 such that all subsequent angles are pi over 3. Okay. So it looks like for this specific vector, we started with 1, 0, we got 45, 45, 90, and then 45, 45, another 90. On average, it was 60. But could it be that these angles might be different if we don't have an input of 1, what was it? We started with 1, 0, I believe, and this is what we got. Okay, so this was just a small exercise